Okay, hi, so we're going to do the fundamental theorem of calculus. There's a couple different forms of this, like a first fundamental and second fundamental, and we're just going to go through it in a rough overview so we can apply it. So the first one is, let's say f, your function, right? Let's say f is your function, is continuous. Okay. And that f is any function that satisfies f prime of x is equal to f of x. Right? What does that mean? It means capital F, the derivative of capital F is little f. Okay? The derivative of capital F is little f. And the integral of little f is capital F. So we have this rule. The rule is then the integral of a to b of f of x, right, dx is equal to capital F of b minus capital F of a, a definite integral. So we've seen this before, and the idea is that if I take the integral of something, say from 1 to 2 of x squared dx, the f is the antiderivative of x squared, which gives us x cubed over 3. And we're going to plug in our a and b, which is our b and our a. Our b and our a. So we plug in b, which is 2 cubed over 3 minus 1 cubed over 3. Now, just to prove that this is true, look up here. The derivative of f should give us back to, derivative of capital F should give us back to lowercase f. So if I take the derivative of capital F, which means we're taking the derivative of this function, x cubed over 3, power rule, that becomes 3x squared over 3, x squared. Now, the big takeaway is that if I take the integral of the a and b value, we can just plug in into our capital version, our integral version, and we just plug in our b and our a. Okay, so that's pretty self-explanatory. Now the second one is a little tougher, and we're saying if capital F of x is equal to the integral of a to x of f of t dt. Now we're going backwards. Before we said f prime of x is equal to f of x, right? Now, if I go backwards, if I take the integral to both sides, it should just be regular capital F. And that's kind of what we get here. So how does this actually play out as an example? If I wrote something like integral of a to, let's give a number like 3 to the x f of t dt, right? Well, that's just some number, any number you want. This is equal to f of x, whatever it is. Okay, just a number. Now, what happens if I take the next step and I take the derivative of both sides? Oops. Well, we wrote this before. We said the derivative of f, isn't that the same thing as us saying f prime? Sorry, not that one. F prime of x. Okay, that's the same meaning. So what should this side equal to? According to our rule back here when we first started, this side, right? We wrote this originally. Shouldn't this side equal to fx? So the derivative is equal to d over dx integral of 3 to the x f of t dt is equal to just f of x. Plug it in. What happens to the 3? Goes away. In all practical applications, it goes away. Now, why does it go away? We're going to actually mix both our rules together right now. When I mix both rules, take a deep breath, and we're going to do this in parts. df over dx. What happens to this 3? What happens to the, and why is it just f of x here? Well, I'm taking the derivative of the integral. So let's actually take our time. Let's actually take the integral first. By our rule, this is equal to the capital F of x minus capital F of, was that, is that how we wrote it? We wrote it up here, right? The integral is capital F. So I'm commenting that exactly here. Okay. So the derivative of capital F is equal to the derivative. Now, what happens when I take a derivative of a subtraction problem? Do I do them together or separately? Remember, it's separate. So I take the derivative and then minus the derivative. Now, what is f of 3? Is f of 3 a variable, or will that be a constant value? What I mean is, if I took some function f and I plugged in 3, do I have an example here? I say f of x is equal to 2x plus 1. That's a variable in the equation, but is f of 3 a variable or a constant now? Isn't that just a constant? And what is the derivative of any constant? 0. So what happens is, looking back up here, when I take the derivative of an integral, this constant value is a plus 0. Oops. Plus 0. Because the derivative of any constant would just be 0. So we're left with, back to our definition, the derivative of f prime is f of x. In actuality, it's going to be d prime of x. Oh, dx over dx, sorry. And dx over dx, chain rule, it's going to give us 1. Okay, let me pause here. Okay, so why is this important? We came up with this huge thing back here of taking the derivative of an integral. Well, think opposite of multiply is divide. Opposite of add is subtract. And in essence here, the opposite of a integral is a derivative. So if you look here, we take the derivative of an integral, that all goes away. And we're just left with the x, f of x. So we're going to show this in application. What happens if I take the derivative of a problem, give myself 665, making it up, to x of 3t plus 2 dt. The answer is 3x plus 2. Done. d over dx, integral of negative 42 of x of sine of x, sine of t, dt is sine of x. Done. Because what does a derivative and integral do to each other? In essence, they should cancel out. And what happens is the variable gets plugged in. Now, if we actually do the problem out, you might say, Michiko, what matters about the 765 and the negative 42? Well, what's a derivative of any constant? Because if I plug this in, let's go ahead and do this equation here. Let's say if I actually went ahead and took the integral, d over dx, integral of 3t plus 2 is 3t squared over 2 plus 2t. We're going to plug in x to 765. We plug in the x, 3x over 2 plus 2x minus our 765 squared over 2 plus 2 times 765. Okay, but aren't we still taking, sorry, that's not equal sign. Aren't we still taking the derivative of this? What's the derivative of, I almost copied it. What's the derivative of 3x squared over 2? That's just 3x. What's the derivative of 2x? Just 2. That looks like your answer. But what about all this left over in the back? That's all just a constant. It was going to go away anyways. So this is what one of our rules allow us. Now the AP exam, if this was for response, it could give you something like this. They would ask you a dumb question like this. That's if x was simply x. But what if it wasn't x? And that's what we're going to show next. So first things to realize, if you're taking the derivative of an integral, it goes away. And we're left with just plugging in the variable. Okay. So to go back and talk about basic derivatives, if I ask you this question, d over dx of x squared, you would go do power rule first. 2, copy the inside. 2 minus 1 is 1. Write a 1 here. Write it, don't write it, it doesn't matter. And then we write this. The derivative of x with respect to x. And normally we just ignore that. Don't we just say that's really just 1, which is just 2x? But if I switch the variable, just to talk about it, d over dx of y squared. where the variables are not the same. Not the same. You would still do power rule. It would still be 2y to the 1 power, and then you try to take the derivative of y, and you realize you can't. It doesn't cancel out. Dx over dx up here did. Dx over dx is 1, but dy over dx does not cancel out, and we're left with this answer here. When you guys learn chain rule, if I wrote d over dx of sine squared x, we took the power rule first, minus 1, and then you do chain rule, the derivative of sine of x with respect to x. And this is really sine of x. And then derivative of sine was cosine of x. And then you have to chain rule on the x. So dx over dx, which is 2 sine x cosine x. And then times 1, which we don't write. Okay. Now, this idea here of having to do chain rule, is actually what we're going to focus on. Because when you have problems that don't look right when it comes to the fundamental theorem of calculus, d over dx, integral of some number, doesn't matter what the number is, to x squared now. How does this problem play out? Let's go ahead and write something like, let's use sine. Oh, I'll keep doing that. T dt. The rule that we showed before was d over dx, integral of x, sine of t dt. This would simply be sine of x. Just plug it in. Those cancel out. Okay. But does that not work here? Can we just plug it in? Well, the reason why we could just plug it in here, because what's the derivative of x? Isn't that just 1? Now, if I went ahead and did this problem, it would be the integral of sine is negative cosine, d over dx, negative cosine of t, some number and x. We rewrite it as the derivative of negative cosine of x minus a negative cosine would be plus cosine of some number. This is some constant. And when you took the derivative of cosine, what's the derivative of cosine? It's negative sine. So negative sine of x. And then you would do chain rule dx over dx. But we don't write that, do we? So we just write sine of x, which is what we end up here, because this part's 0, right? But us doing the same problem here actually changes. If I take the integral of sine, that gives me, like what we wrote before, negative cosine t, some number, and x squared. Is everyone okay? Looks very similar, very similar. We plug in our value, d over dx, negative cosine of x squared minus a negative cosine becomes a plus cosine of a number. Very similar, except one slight difference. See that slight difference? Now when I take the derivative of cosine is negative sine, negative sine of x squared. Chain rule, the derivative of x squared is 2x, and the derivative of a constant is 0. Turns out our answer is sine of x squared. Now let's go back and rewrite this. Oh, 2x. Go back and rewrite from start to finish. We started off with the derivative of the integral of some number, x squared, of sine of t dt. And we ended up with the answer sine x squared times 2x. before you come up with an idea of maybe you spot it, maybe you caught it, let me give you another quick example over here. D over dx integral of 4x cubed of, making it up, let's say it's cosine of t dt. Can you make a guess of what the answer would be? An answer within like 5 seconds? Cosine 4x cubed. Right, that's what we thought it was going to be. 12x squared. We gave you a problem. D over dx integral of sine of x of x squared. No, sorry, I will say x. T squared dt. Can you make a guess? Where does the sign go? This answer is sine squared x cosine x. So hopefully you caught the pattern. The pattern is like what we did before. X became t, or t became x. So whatever's up here gets plugged in. And after we plug it in, don't forget we need the chain rule of it. Once you plug it in, don't forget we need the chain rule of it. Once we plug it in, don't forget we need the chain rule of it. And that's what we did back here. Because once we plug it in here, and when we take the derivative, you always end up with the chain rule of it. And that's our rule. Okay, one more example of the fundamental theorem of calculus. And what if, instead of a variable and a constant, it's actually two variables. So we take the integral, we'll say x to x squared t over dx of something we don't really care about, t dt. Okay. Well, we have a rule that goes like this: a to b of f of x plus b to c of f of x is equal, we go from a to c. You guys remember this one? Okay. I can separate and add integrals as long as, one, it's the same function, and two, you continue where I left off. And the application of this is that if we say an integral is cumulative change, I give you a function, f of x, and this is a, this is b, and this is c, and the integral says how much area, how much stuff is under this curve. How much stuff is under this curve? Well, if you go from a to b, right, you go from a to b, and this guy goes from b to c, from b to c, can you just tell me to go from a to c in total? So what we're going to do, we're going to split this function into two separate ones, where this b value is just some constant in the middle, just some constant. Doesn't matter. So d over dx, this becomes, sorry, we're going to separate our integral from x to a sine t dt plus integral from a to x squared sine of t dt. We do not like this order. let's go back and take a look at my rule. My rule always goes, where's my rule? Oops. My rule is here. If you look here, it goes from a constant to our variable, constant to our variable. Always from our constant to our variable. The rule is going the wrong way. We need to swap those around. So d over dx. And if you remember, how do I swap our interval? Just a negative sign. Negative integral a to x sine t dt plus integral a to x squared sine of t dt. Now, if we take the derivative to write it out, d over dx, integral from a to x sine t dt plus d over dx, integral a to x squared sine of t dt. How I was able to split, distribute, quote unquote distribute, please don't call it that, but we're able to, when I'm taking a derivative of a plus or a minus, you can take a derivative of them separately. That's the reason we can do that. And our last step is, hey, what is this guy? That's back to our fundamental theorem. Negative sine of x, just plug in the x. Plug in the x squared, don't forget chain rule. Sine of x squared, 2x. So again, if you end up with two variables, you have to split it. And when you split it, make sure you do go in order from x to some value in between, from that value in between to the b value, a to b, from starting to ending, and then flip it, and then you can plug it in.